Swayam Prabha. Digital India. Educated India.
Having made some introductory remarks about the ceramic materials in general and differentiating between traditional ceramics as well as advanced ceramics, and also giving you some idea about the compounds, the particular chemical compounds, whether they are ionic in nature or covalent in nature, which are known to be ceramic materials, which are used extensively as ceramic materials. Our next course of discussion will be on the structure property relationship. In fact, throughout this course we will be taking up the structure of different materials and these structures how they give rise to different properties. That will be one of our major points of discussion. So, to start with, let us try to understand what we mean by structures, particularly the crystal structures, and what are the different structures in which many of these oxides or ceramic materials in general crystallizes. In fact, by structure we are meaning at this point of time it is the crystal structures or the atomic arrangement of the different elements present in the particular compound. So, we will be discussing about the crystal structure of different oxides as well as other compounds, but before that let us see what kind of atomic arrangement we can expect in different kind of solids. Here we are discussing about the close packing of atoms. For our purpose, we will be always discussing or we will be considering the atoms as solid spheres, so that we can understand their geometry and the kind of packing they can have under different conditions. In this case, we have two layers of atoms. One is the white layers, there are closely packed, in fact closest packing, they are brought together as close as possible without any further compression or any further closing by. So, they are touching each other. In fact, these are spheres. Of course, in the 2 dimension we are seeing only the circles. The circles are touching each other. So, around a particular atom or a circle there are 6 such circles, so that they come close to each other. In 3 dimension you will have number of layers of such close packed layers, close packed arrangements. So, while the white ones may be the base one, base layer, on top of that there is another layer, the black ones. So, the black ones have been placed over the white ones, but they are not exactly on each other. So, the black ones not exactly vertically over the white ones, they are actually placed about 120 degree the rotation. So, that on the trough prepared or made by the arrangement of the first layer, the top layer sits. As a result, you get different kind of interstitial spaces. Okay. So, you have the bottom layer as well as the top layer, and in between you have some interstitial spaces. Now, the interstitial spaces, around each interstitial spaces the number of atoms are actually not equal. In some of them we have what we call a tetrahedron. A tetrahedron is formed by making a close packing arrangement of the bottom layers, these 3 are in the bottom layer, and this one is on the top layer. So, in between you have a space, you have a space which is not filled up by the atoms, whereas there is another kind of space is also created, interstitial site is also created by the same structure or the same arrangement of two layers, two close packed layers, in which you will see a bi-pyramid kind of thing. In the middle layer you have 4 atoms. These 4 atoms are in the middle layer touching each other. Of course, for our clarity we have not shown them as touching each other, but actually in this structure they are touching each other. Whereas, even if they are touching each other at the surface, you will get some space in between, and that is another kind of interstitial space, and in this case the number of atoms surrounding this particular interstitial space is 6, not 4, and this is called the octahedral site, or the particular interstitial site has a octahedral coordination. So, this is actually the coordination number of this interstitial site is 6, whereas there is another set of interstitial sites which has a coordination number of 4. In this case it forms a tetrahedron, in this case it forms the atoms forms a octahedron. So, the coordination number in this case is 6 and the coordination number here it is 4. This has been a exploded view of this tetrahedron is shown here, and a exploded view or the actual size or actual arrangement of the octahedron is shown here. So, this is the octahedron and this is the interstitial site which is magnified in this part of the diagram. Here it is the tetrahedron or tetrahedral site which has been magnified here. So, we have two different kind of interstitial sites created by bringing together two close packed layers. So, that is one of our primary consideration for understanding the structure of different materials and different oxides in general. So, the coordination number, the definition of the coordination number is like this, which has been just discussed. It is the number of atoms or ions which surround a particular atom or ion or the inner interatomic space. So, this it may be space or that particular space may be occupied by a second atom or second ion. So, the coordination number refers to the site, or if the site is occupied by a particular atom or ion, the coordination number refers to that particular atom or ion. The most common values of coordination number are 4, as you have discussed in case of tetrahedron. If it is octahedron, it is 6. There may be some arrangement where the coordination number, particularly a cubic arrangement, the coordination number is 8, and there may be a situation where the coordination number can also 12. We will look into these possibilities later on, but these are different kind of coordination numbers, and these are the polyhedra formed around that particular space, the tetrahedral, octahedral, cubic or dodecahedral. So, this kind of coordination number we will be discussing this coordination number time and again when we discuss the structures. These are another way of looking at the same layers. Here instead of 2 layers we have 3 layers. This is the bottom layer, it is a little bit of 3 dimensional view. This is the middle layer on top of that, and there is another layer, a third layer on the top of the second one. Okay. So, they are all touching each other either both in the vertical direction and in a horizontal direction. So, that is what we call the closest packing possible. Now, when you put the third layer, there are actually 2 possibilities. There is a off center when you put the second layer over the top of the first layer, the second layer is here, where the first layer is slightly off center, and third layer you can see here it is exactly vertically above the first layer. In this particular structure, the third layer may have the vertically exactly vertically above the first layer. Okay. So, if we call this layer as A layer, middle layer as the B layer, the third layer, the top layer, we can call it A layer, which is equivalent to the A layer. So, in a stacking arrangement, as if the whole structure, the whole space is being filled up with the atoms arranged in a particular manner, and if we stack one after the other, one layer after the other, then this is a layer, this is B layer, and this is again a layer, which is equivalent to the bottom layer. So, this arrangement gives rise to a symmetry, and you can draw this kind of a geometric, 3-dimensional geometric body, or in short we can call it unit cell, which actually can repeat itself in all the 3 different directions to fill up the complete space. So, this particular geometry is a what we call the hexagonal geometry or hexagonal close packed arrangement. The atoms are arranged in a hexagonal close packed arrangement. So, for clarity, this has been shown here as smaller atoms, they are not touching each other in this direction, but in actual practice, in reality they are touching each other. We are just trying to represent the same picture over there. So, you have a hexagon on the top, another hexagon on the bottom, and the second the middle layer is actually not forming a hexagon, but it is a triangle. So, they are in between the hexagon, top hexagon and the bottom hexagon. Okay. So, there are 3 layers, 3 atoms, of course, within this particular volume of the solid, and then these are in the form of a hexagon. So, that is the reason we call it hexagonal close packed arrangement. There is another arrangement, it is also a very simple geometry. In this case, of course, the layers are slightly inclined. Layers are not horizontal layers, but you can see this is one layer, the green one is one layer, blue one is another layer, and the orange one is another layer. Okay. Orange has one layer, only one atom, other atoms are missing here, has not been drawn. The green one is there are 6 layers, 6 atoms, and this also has a 6 atoms, but it has been in a different orientation. Whereas, the bottom one, there will be another bottom one which is equivalent to the orange one on the top. So, actually there are 4 layers in this compared to 3 layers on the top. So, if we take this as A layer, this becomes B layer, and this is a not equivalent to the A layer. It is not vertically above the E layer, in fact, it is a third position where it can go. Okay. So, it actually goes to a third orientation, and it is becomes A layer, B layer and C layer. So, it is a ABC packing, and this orange atom and the orange atom down are equivalent. So, although there are 4 layers we have arranged, but actually 3 of them are distinctly different and one is equivalent to another one. So, 4 layer forming a stacking of what we call ABC stacking. So, this ABC will repeat itself. In this case, the earlier one, the hexagonal one, AB will be repeating, whereas in the bottom one, or in the case of cubic arrangement. So, the symmetry here is not hexagonal, the symmetry here is cubic, and it is face center, we call it face center cubic. Why it is called face center cubic? These are forming a cube, at each corner you have atoms, and also at the center of each face, if you draw two diagonals on each of the faces, at the center of each face there will be another atom. So, this is another way of representing the same structure. Okay. It is not in the form of a stacking arrangement, but in the form of a unit cell, what we call the unit cell, and this is a smallest unit of that volume, which can repeat itself in all the three different direction, A, B, C direction, and fill up the complete space. So, in case of this arrangement, this hexagonal unit cell will repeat itself, whereas in case of this ABC stacking, the cubic arrangement will repeat itself. So, from the same close packed structures or close packed atoms, just by reorienting or rearranging themselves, you can have two different symmetries. One is hexagonal close packed, another one is face center cubic. The volume fraction occupied or the open space in both these structures are same. If you can calculate what is the volume fraction of the space which is empty because of this curved nature of the atomic surfaces, there will be some empty space, and that empty space is exactly same because both of them have the close packed arrangement. So, that also you have to remember, although their unit cells are different, the basic symmetries are different, but just because both of them have the close packed arrangement, all the atoms are touching each other in the closest possible manner. Therefore, the volume fraction occupied by the solid is same, or in other words, the open space available is also same. These are few other arrangements which may not be completely close packed. Okay. The opens they may be touching on one particular direction, the atoms may be touching in one particular direction or more than one particular direction, but they may not be touching in all the directions. So, in some layer they may be touching each other, in others they may not be touching each other. So, they are relatively open structures, but they have also certain amount of symmetry, and this is another kind of symmetry or the arrangement of atoms in which some compounds may be available. This is what we call simple cubic. Simple cubic is nothing but you have the cube. If you draw a cube, at each corner of the cube you place one atom, and that will give you the simple cubic structure. And if you can imagine, you will find that it is not fully close packed, it is relatively a open space. There are some more open space in the structure, in the arrangement, than what we get in a close packed structure, which we discussed earlier. There are another open structure which is called body centered structure. Again, it is a cubic symmetry. You have 8 corners are occupied by the atoms. In addition, at the center of the cube, or where the 3 body diagonal intersects, at that point also you have another atom. So, that is the reason this particular symmetry is called body center symmetry or BCC. So, HCP, FCC, then SC simple cubic, and then body center cubic or BCC. These are 4 very important structures in which the materials crystallize. Now, if we take a cubic symmetry, we have seen earlier, this is a cubic symmetry, the green ones are the cubic symmetry, and in fact, it is not only cubic symmetry, it is actually face center cubic symmetry, a close packed face center cubes. So, you will have 14 in all 14 green atoms or green ions, in which case there will be some interstitial spaces. As you have discussed, some of them will be 4-fold coordination or tetrahedral coordination, and some of them will be octahedral coordination. So, any closed packed structure you will have basically two different kind of interstitial spaces. One is surrounded by 4 atoms, in another it is surrounded by 6 atoms. So, in a structure of FCC or face center cubic in this case, which are the positions where these interstitial sites are available, and it has been found, or one can very easily visualize, that if this cubic structure is a closed packed structure, that means these atoms are actually touching each other along the diagonal of the face. Okay. This is the, although for clarity they have been drawn separated from each other, but in practice actually they are touching along this line. They are also touching along this line, along the face diagonal, the other face diagonal. In fact, similarly in along all the face diagonals, these green atoms are actually touching each other. If so, but they are not touching along this line, along the edges, what we call the edge of the cube. They are touching along the face, along the diagonal of the cube, face diagonal actually. There are two types of diagonals in these structures, one we call the face diagonal, other is the body diagonal. Body diagonal means this, if this atom touches this atom, or a line is drawn from this atom, this corner atom to the next or the opposite corner atom, then it passes through this center of the cube, and that is what we call the body diagonal, and a diagonal drawn on the face is called the face diagonal. So, in this case they are not touching each other along the body diagonal, but these green atoms are actually touching along the face diagonal. If so, it is not touching along this edge. Okay. These two are not touching because they are touching on this side. So, they cannot come closer than that. So, there will be some space or interstitial voids, we call it, this is an interstitial void. Similarly, on the middle of each edge of the cube, there will be interstitial voids which are shown here by an yellow circle or yellow sphere. So, these yellow spheres are all actually voids in the interstitial sites, in some space in between the actual atoms. So, these interstitial sites which has been shown here by yellow circles, they are actually the coordination number of those interstitial sites are actually 6. There is not 4 coordination number, 4 coordination number are not shown here, but they are actually present. We will see how, where exactly the coordination number of 4, the interstitial sites with coordination number of 4 actually resides. So far as this structure is concerned, cubic structure, the edge diagonal, edge centers are the places where you have interstitial sites. In addition, of course, another interstitial or the 6-fold coordination, octahedral interstitial, are present also at the body diagonal, body center, or the center of the body also has a octahedral site. In addition, there are 12. Okay, there are 12 edge centers. Okay. So, in all there are actually one, if you calculate what is the number of atoms, what is the exact number of atoms in this particular cell, in this particular unit, you will find there are 4, effectively there are 4 atoms, 4 green atoms per unit cell. Why? One can find out this is actually at the corner of a cube, and if you want to fill up the space, there will be 8 such cubes which will join at this point, okay. 4 on one layer and second and another 4 on the top layer. So, each of these corner atoms or corner ions are actually shared by 8 unit cells. So, 8 such unit cells are joining at this point, 4 on the one layer and 4 on the just layer above. So, therefore, the contribution of share of this particular atom to one unit cell, which is shown here, is actually 1/8. Okay. So, 1/8 into 8 corner atoms. So, the total contribution or total share of this unit cell, so far as the atoms are concerned, from the corner atoms is only 1. Whereas, if you consider the face center positions, these atoms, they are shared by 2 unit cells, one this one and there will be another on the top. So, that will be placed on the top and therefore, that half of it will go to that unit cell and half of it will be in the bottom unit cell. So, the contribution or share of this particular unit this particular atom to this unit cell is only half, and there are 6 on 6 different faces we have 6 such atoms having a contribution of share of half. So, that makes 3 and this also this 8 atoms contributes only 1. So, the total contribution the total volume shared by this particular unit cell of the atoms is only 2. Okay. So, there are 2 atoms per unit cell, we call it 2 atoms per unit cell, although it has been shown large number of atoms, about 14 different atoms are seen here, but actual contribution to this particular unit cell is only 2 and rest of it is actually being shared by the neighboring unit cells. You can make some similar calculation with this interstitial spaces. How many such interstitial spaces are available in this unit cell? One can find out there are also 2. How? One can see these are on the edge, center of the edge. How many unit cells are sharing this particular atom? You will find there are 4 atoms, 4 unit cells are actually sharing this particular site. Okay, this is an interstitial site. So, all these 12 are shared by 4. So, each one is contributing actually 1/4. 1/4 into 12 is 3. So, these sites are actually shared by 4. So, 12 sites are shared by or the contribution to this particular unit cell is 3. And in addition, we have also seen that at the center of the cube, center of this particular cube, you have another site. This site is completely inside this unit cell, it is not being shared by any other neighboring cells, neighboring unit cells. Okay. So, this is 1, its contribution is full. So, 1 plus 3 once again it is 4. So, there are 4 actual atoms occupying the sites and there are 4 interstitial sites, octahedral interstitial sites within that unit cell within that structure. So, there are equal number of atoms and octahedral unit cells. Okay. So, that is another very important characteristics of the so called close packed structure, whether it is hexagonal close packed, whether where we have 2 layers or it is a FCC or face center cubic close face center close packed structure or cubic close packed structure. There are equal number of atoms and the interstitial sites, the octahedral interstitial sites particularly. If you talk about the tetrahedral interstitial sites, it is little difficult to imagine where exactly the tetrahedral interstitial sites, but you have to accept my saying that these tetrahedral, all the tetrahedral interstitial sites are within this unit cell, within this unit cell, not being shared with the neighboring unit cells. Okay. And if you draw a body diagonal, then there will be two interstitial sites on that body diagonal. It is about 1/4 from each corner. Okay. So, if you draw a body diagonal from this atom to this atom, then there will be one somewhere here, okay, one somewhere here, which is about 1/4 of the total length of the body diagonal, and similarly 1/4 from the other side. Okay. So, there are 8 corners, 8 corner atoms, and corresponding to 8 corner atoms there will be one tetrahedral site about 1/4 distance of the total body diagonal length. So, from this corner there will be one tetrahedral site here, and from the other side also there will be another tetrahedral site somewhere here. Okay. So, corresponding to each corner atoms there will be one tetrahedral sites. So, 8 corner atoms, and all of them, the tetrahedral sites are within the unit cell, and therefore, it is not, they are not shared by the neighboring atoms and neighboring unit cells, and therefore, the contribution of all the 8 is to this particular unit cell, and therefore, the total number of tetrahedral sites actually 8. So, in essence what we are saying, in any closed packed structure the number of tetrahedral site is double the number of atoms present. So, there are equal number of atoms and the equal number of and the same number of octahedral sites, and double is the number of the tetrahedral sites. So, that is also another very important consideration when you are talking about the geometric pattern of different oxides or different other compounds. With this background, let us go to look at some of the actual examples of oxides, some simple structures of oxides and few other compounds. How we can derive, how we can visualize some of these structures, the atomic arrangement in some of these oxides. Now, the basic difference between an element like metal, iron, nickel, cobalt, these are only elements and they are present in the form of element. So, there are only one kind of atom, okay, either iron atom or in another case a cobalt atom or maybe copper atom and so on. So, for all metals there are only one variety of one size of atoms. So, whatever we have discussed earlier, that very well applies, these structures very well applies to these metals, because we can have only one variety of atoms, and we have discussed so far only one variety of atoms. Others are of course interstitial sites, okay. They are not occupied, they are just the interstitial sites, the voids. In fact, iron, the metallic iron has few polymorphs, they have different structures at different temperature ranges. So, mostly at room temperature it has a BCC structure, body center cubic structure, whereas in a slightly higher temperature it has a FCC structure, that phase center cubic structure, right. So, copper for example has a hexagonal structure, not a cubic structure, it has a hexagonal structure and so on. However, when we are discussing about oxides, we have to deal with two different ions, one is cation and another is anion. In an oxide of course, the anion is always oxygen or oxygen ion, but there will be different kind of metals or metal ions present in different kind of oxides. And you may very well imagine that their sizes are different. Okay. Cation is a smaller ion than an oxygen ion. Okay. The oxygen ion, the ionic radii of oxygen is about 1.4 angstroms, whereas most of the metals has a ionic radii which is less than 1 angstroms. So, there is a big difference between the ionic sizes of cation and the anion. So, that makes our life little simple in a sense that cations actually resides in the interstitial sites created by a closed packing, either closed packing or a open space created by the arrangement of anions, or in this case, in case of oxides, it is the oxygen ion. So, oxygen ion forms a kind of skeleton, and this skeleton has, because of particular spherical nature, it is inherently it has some interstitial spaces, and these interstitial spaces are being occupied by some of the cations, and that is how an oxygen structure, oxide structure is built up. So, we consider this particular arrangement, these particular situations. These white circles are actually oxygen ions, they are larger ions, and the black circle is a cation, is a metal ion, and it is a smaller ion. Normally, they will go and sit in the interstitial site created by the atomic arrangement or the oxygen of the atomic arrangements of the oxygen ions. Now, there are three different situations here. You can see, let us start from there on the right side. You will see 4 oxygen ions are touching each other along their diagonal. Okay. If you form a square, so if you form a square, so this you add this and then it forms a square. So, if you just join the corner or the center of all the 4 atoms, they will form a square. Now, if you have that, then you have some open space here. So, this is your interstitial site. In this case, this interstitial site is basically have a 4-fold coordination, you can say. There are 4 atoms surrounding that particular site. Well, then you can introduce one cation here. Now, what kind of size you can have? This size may not be exactly fitting to the size of the interstitial hole. Okay. So, it may be little smaller or little bit larger. In this case, the cation is slightly smaller. Okay. So, before they can touch on this direction, these circles are touching on this along this line. So, there is a gap, and this is called, or this according to the structural requirement, this is an unstable structure. This is not a very feasible structure. Okay. So, a cation cannot go inside, and therefore, in an oxide you may not have this kind of a situation. In any compound you may not have this kind of situation, it is more unusual situation and unstable situation. You can have these kind of situations. One is the diameter of the cation is exactly matching with the highest diameter of the interstitial site. So, the atoms are touching along this line, along this point and this point, between them the oxides are touching each other, and the cation and the anion is touching along this line. So, the exactly size of the cation exactly matches with the size of the interstitials, or the maximum size of the sphere which you can introduce into that interstitial position. So, this is one situation which is a very stable situation, and there may be another situation. Other situation, this is little bigger. The cation is bigger than the actual size here. If it goes and sits in the interstitial site, then it will push back these oxygen ions. Okay. So, the oxygen ions no longer touching along this line or along this line or this line, but it still remains a symmetry. Symmetry is still cubic, okay, it is form a cube, but even if the symmetry is cube, but they are not touching, they are not fully closed packed structure. So, the atom or the size of the cation is such that it is larger than the critical size, we call the critical size of this particular structure. Okay. So, the oxygen ions are pushed apart and a larger size of the cation goes and sits in the interstitial site. This is also stable, this is possible in any structure, this is possible, but with a limitation. With a limitation, it can push to some extent, it cannot push too much. Okay. So, there are energetic considerations based on which one can find out how much it can be pushed. Normally, the size maybe is about 15% more than the critical size, okay, 15 to 20% more than the critical size, not more than that. Okay. So, this is not possible at all. It will go, it does not mean that this particular metal having a smaller size cannot form an oxide, it can still form an oxide, but its structure will be different. Okay. Its structure will be different, may not have a closed packed structure like this, or it may not form a compound with oxygen, it may form compound with something else. Okay. So, normally these kind of structures are not possible, but these two structures are possible. Keeping this thing in mind, one can go to many different situations. So, there are consideration of ionic radii, which actually controls which particular kind of coordination, which particular kind of arrangement becomes stable in a combination of cation and anion, okay, and that is very important. So, there are maybe depending on the cation size and the anion size, different structures will be stable and the structures may change depending on the size of the cation and the anion. So, there is a what we call a critical radius ratio for each of the coordination numbers. For each of the coordination number, we have a critical radius ratio, below which it is stable or above which it is stable, below which it is not stable. So, there is a list, there is a one can find out from very simple geometry, solid geometry, which for which kind of coordination, which what ratio is the critical one. For example, we have several kind of arrangements. This is a linear arrangement, you can say there is two cations, two anions here, in between a cation. Well, that kind of arrangement can always be there. There is no restrictions from the point of view of the geometric pattern. Okay. So, this is anything less than 0 is always have that this kind of a coordination, but these coordinations are in general not feasible, not possible. So, we need not consider that, that is not very important. Triangular coordination, that means we have a threefold coordination. This is a twofold coordination, this is a threefold coordination. Once again, for triangular coordination, it is on a plane, it is not on different levels, this is on a particular plane, 3 atoms are there on the same plane, and also the cation atoms in the sense the anion and the cation on the same plane. So, 3 atoms are possible, and once the 3 atoms are there, there will be also a critical radius ratio, and that is given in this table. You can see 0.155, okay. That is the ratio of the RC by RA. RC by RA means cation ratio by the anion ratio. The cation is smaller and anion is larger. So, if that ratio is 0.155, then that is the critical ratio for this triangular coordination. or three-fold coordination. Three-fold coordination can exist, as I have mentioned earlier, even if this ratio is slightly larger, the three-fold coordination can still exist, but it cannot be less than this value. So, it can increase, it can push back the larger cations will push back the anions and the cation ratio will increase till it reaches this value 0.225. So, 0.155 to 0.225. Once it reaches, as if the cation size is increasing, keeping the anion size same. So, the total cation the effective cation ratio is increasing from this level or this value to this towards this end. So, between 0.155 and 0.225, the triangular coordination or three-fold coordination will be stable. Okay. Whereas, if it crosses the 0.255 value, this particular critical value, then the three-fold coordination will no longer be stable, it will convert to a four-fold coordination, and that is we have discussed as tetrahedral coordination. So, this is four-fold coordination. So, it has a particular value, four-fold coordination, if the site, the interstitial site, four-fold coordination interstitial site has to be fully occupied, or the cation has to touch each of the four anions, then the size of that cation must be 0.225 or more, okay, 0.225 or more. Less than that, it will convert itself. This particular geometric configuration will be more stable than this configuration. So, this is a four-fold coordination in the form of a tetrahedron. Now, beyond that, if the cation size still increases, anion size remaining same, because we are talking about primarily oxides, the oxygen ion or oxygen cation anion radius remains same and cation increases, then you have next level is 0.414. 0.414, all these things can be calculated very simple way by geometry, solid geometric consideration. So, from four-fold it will change over to six-fold. There is no possibility of five-fold, unfortunately. Five-fold symmetry is not normally possible. Okay. So, there are other considerations for which the five-fold is a forbidden, is a kind of forbidden symmetry element, and therefore, from 4 it will jump to 6, and the critical radius ratio is 0.414. So, if the radius ratio is between 0.225 and 0.414, then you have a stable tetrahedral coordination, okay, four-fold coordination till it reaches this value. If the radius ratio still increases beyond 414, then the octahedral or six-fold coordination will be stable till it reaches another value 0.732. In 0.732, it will change from six-fold to eight-fold coordination, okay, to eight-fold coordination, then it will go to the 0.732 will go to the eight-fold coordination, okay, and beyond that the eight-fold coordination will remain constant until and unless you have RC by RA becomes 1. In 1 it will be a 12-fold coordination, okay. That means radius of cation and radius of anion is exactly same. So, they are indistinguishable and they will form a complete closed packed structure. So, this is a very important consideration, what kind of coordination will have a particular cation in an oxide matrix or an oxide skeleton. So, depending on the size of the cation, it will go to different configuration and different interstitial sites, and that will also change the symmetry in the unit cell and the unit cell dimensions. Okay. So, this is another very important consideration when you are talking about the geometry or the symmetry of the crystal structures. Well, with this background, let us try to look at some of the structures, very simple structures which are possible and which are available in nature. Okay. The very first structure is what we call sodium chloride structure, or the mineralogical name of sodium chloride is actually rock salt. So, this structure in fact is a structure type. We will see later on that many different oxides have this particular structure. So, this is a very typical structure in which many different oxides crystallizes, and what is the description of this crystal structure. There are obviously two ions, one is sodium ion and there is chlorine ion. Sodium is the cation, so it is smaller, and chlorine is larger and it is an anion. Of course, somehow sodium ions and the chlorine ions, their anions, ionic sizes are not too different, they are much closer to each other, but there is a difference. So, this is on the right actual kind of geometric shapes and geometric pattern in which the sodium and chlorine ion are placed. Okay. So, you can see these larger ions are actually chlorine ions. Of course, the colors are more or less same, but there is size difference. So, these smaller ions are sodium and these are chlorine ions. We have seen earlier that these are the centers, edge centers, where a octahedral site is possible, octahedral interstitial is available, right. And you can see the sodium ion are basically at the edge centers. From here also it is seen that of course, this has been reversed. This has been reversed. The edge centers are here, it is sodium ion, and the corners are the sodium ion, and the middle portions are the chlorine ion, and the arrangement is reversed. Okay. Whereas, let us talk about this kind of structure or this geometry, where this is in this cube, the chlorine ion are initially placed at the corners and also at the face centers. For example, here this is in the face center, right. Okay. In fact, you have to extend this cube to that point, this one, although a smaller cube has been drawn. In fact, it might be something wrong. This cube actually extends up to there, this center and this center has to be joined. Okay. So, these are interstitial sites created by the arrangement of the oxygen ions. So, sodium sits in the interstitial sites, and if somebody calculates what is the radius ratio of sodium and the oxygen chlorine, you will find it satisfies the octahedral coordination. So, the sodium ion actually goes to the octahedral coordination, and there are alternate sites actually in this structure. You will find there are in different directions, you will get one sodium, then chlorine, then sodium. In this also, in this direction also, this is chlorine and this is sodium. So, this unit cell has equal number of chlorine and sodium. Sodium and chlorine number ratio is 1:1, and we have found earlier that in a FCC structure, the face center cubic structure or close packed cubic structure, the number of atoms and the interstitial sites, octahedral interstitial sites are same. So, in a sodium chloride, if you just fill up all the octahedral sites by sodium atom, all the octahedral sites created by the arrangement of the chlorine atoms, the octahedral site created by them, if you fill by sodium atom, they will maintain a ratio of 1:1, because there are equal number of atoms and the interstitial sites, octahedral interstitial sites of course. None of the tetrahedral interstitial sites in this case are occupied. So, tetrahedral interstitial sites are empty, whereas all the octahedral sites are completely filled and they have a equal ratio of chlorine and sodium. So, sodium occupies a octahedral site, and you will find here from this structure you will find the both chlorine and sodium. Chlorine is surrounded by 6 sodium atom, and sodium is also surrounded by 6 chlorine atoms. So, the octahedral the coordination number for both these ions are same. Sodium ion has the 6-fold coordination, chlorine also has a 6-fold coordination. So, that is the typical situation in sodium chloride structure, and although we are discussing here the chloride structure, which is not an oxide, chloride is not a ceramics as such, but we are discussing it for the very basic purpose that this particular structure type is available in many of the oxides. Many of the oxides, divalent, particularly divalent metal oxides, all of them do crystallize in the sodium chloride structure. So, that is the description of sodium chloride structure, and let us see what are the different oxides in which actually crystallizes in this particular structure. So, all divalent metal ions like starting from MgO, calcium oxide, strontium oxide, all of them are actually ceramic oxides. They have some high temperature, high melting point, and they are used for different purposes. We will discuss them at a later stage. So, whether barium oxide, strontium oxide, cadmium oxide, cobalt oxide, nickel oxide, all of them are divalent. FeO of course stays in is available in 2 different valency states, 2 plus and 3 plus. TiO, TiO2 normal valency state of titanium is 4 plus, but TiO is also available, this is another stable state, NBO and VO. A few of the sulfides also possess this structure, they are FeS and NiS. Of course, sulfides we will not be discussing too much about it, but so while you are discussing the structure, there are different compounds having the same structure, the description is same. Okay. Oxygen forms, in all these cases oxygen forms a close packed cubic structure or FCC structure, phase center cubic structure, close packed cubic and phase center are equivalent. So, and magnesium or the metal ion goes to the octahedral interstitial, and the ratio atomic ratio or the ionic ratio remains 1:1, and that also satisfies that all the octahedral sites and the number of atoms are actually 1:1 in this particular structure. So, this is the description of sodium chloride structure, and it is a very very important structure so far as the oxides are concerned. Next, there is a structure which is called cesium chloride, just like sodium chloride. This is another alkali halide, okay, and another alkali halide. So, this has a cesium chloride structure, but it is more of a open structure. Okay. You can see cesium ion is much smaller than sodium ion. So, sodium ion, it does not form the sodium chloride structure, although they are chemically they are very equivalent, chemically they are more or less same, both of them are basically an alkali halide, but just because this ionic radii are different, the structure is different. Here the chlorine ion is much bigger and it sits at the center of the cube, whereas the cesium ions are at the corner of the cubes. So, both together actually forms a kind of body center cubic structure. So, at the center is a chlorine ion, and at the corners of the cube is cesium ions. So, it is different from the sodium chloride structure. Chemically they are same, but structurally they are different, primarily because the ionic radius ratio is much different. Okay. So, with this we stopped here. We have discussed some of the basic features of atomic arrangement, how the symmetry comes, what kind of interstitial positions are created by a closed packed structure. We have two different kind of closed interstitial, one is basically tetrahedral or 4-fold coordination, the other is 6-fold coordination, and then with oxides, which are because they have two different ions, one is a cation and the anion, anion is much larger than the cation. So, normally we describe the oxide structure by filling up the interstitial sites by the appropriate size of the cation. So, that is how we will describe or we will discuss more and more oxides in the next class. Thank you.